All right, so we are continuing our discussion of line integrals, and we're going in to talk about a new topic. So just to recap what we did last time, it's the same topic actually, just looking at some different strategies for it. So just look at what we did last time. We discussed two different kinds of line integrals. The first kind of line integral is a line integral of scalar functions, and the notation here I'm using is in 2 dimensions, but the formulas on the right-hand side in both of these cases are exactly the same. Literally, symbolically, they're the exact same thing in 2 dimensions or 3 dimensions, so it really doesn't make a difference. But either way, we're looking at scalar functions or vector fields. So you can either integrate scalar functions or vector fields. Now, the good news is that these formulas, in theory, will always work. In theory, they'll always give you the answer that you want, but in practice, this is the bad news, in practice, if you're trying to find the vector field integral, if you're trying to find the line integral over this vector field, then there are instances where that curve or that vector field are so awful that that can be really difficult to do, perhaps even computationally impossible. So you can't always do that. Now the good news again, there are some tricks that we can use in certain special cases. And really, there are 2 special cases for line integrals that we're going to take a special close look at over the next couple sections. So the first special case is what happens when your vector field f is actually the gradient of some other function, little f. We call that a potential function. Or on the other hand, your curve C is a closed loop. It turns out that if one of these 2 things is true, there are different tricks that you can use to make your lives a little bit easier. So let's take a look at what that can actually look like. So in particular, today I want to look at the case where we have that our vector field is in fact a gradient field for some scalar function f. Now yesterday we defined that this means that f is a conservative vector field. Now what this means in physics is that if you interpret f as a field of forces, like gravity or electromagnetism or fluid flow, then that force field results from some potential energy function f, little f. Now, mathematically speaking, we say that f is conservative when it has a potential function, little f, so that the gradient of little f is the vector field, big F. And sometimes we call little f a quote-unquote anti-gradient. Which makes sense because it's the, if you take the gradient of little f, you get the vector field, and little f is our anti-gradient in that sense. Now, there's a, now what happens when you do this? Well, I want to point out that, and I mentioned this a little bit yesterday, not all vector fields have anti-gradients. Now, all continuous functions have an antiderivative. Now that's the good news. One formulation of the fundamental theorem of calculus, all the way back from Calc 1 and Calc 2, is that if you actually define the function big F of x is the integral from a to x of little f t dt, that is an antiderivative of little f. It might not be a pretty antiderivative, it's not a very nice antiderivative, but it's still an antiderivative. Which is to say that if you take the derivative of that big F, you're gonna get little f. That's a well-defined function. It could be an ugly well-defined function, but it's still a well-defined function. Problem is, not every vector field is conservative. So now if you take, for example, the function little fx equals e to the x squared, well, that does not have an antiderivative in terms of elementary functions, meaning you can't write the antiderivative of that thing in terms of sines or cosines or exponentials or logs or powers or anything like that. It doesn't work. There is no nice set of functions that will give you e to the x squared as an antiderivative. On the other hand, the function, the integral from 0 to x of e to the t squared dt is an antiderivative of e to the t squared, e to the x squared. So that does work. That's still an antiderivative. But meanwhile, we looked at the vector field yesterday, fxy is y comma negative x. And that doesn't have an anti-gradient at all, which is not to say that it doesn't have an anti-gradient that can be expressed in simple terms. That I'm not saying that yeah, it has an anti-gradient, but it's just really ugly. No, it does not have one. It does not exist. So that's going to cause some issues if you try to do certain kinds of analysis on that. So the point here is, conservative vector fields that have an anti-gradient, those are very special. Those are very special vector fields. And we're going to take a look at what some of the outcomes are for those special conservative vector fields. And it has to do with this thing called the fundamental theorem of line integrals. The fundamental theorem of line integrals involves, well, that's what you get when you take the integral of a gradient vector field. And what it tells you is that the integral over the gradient field is the evaluation of your original function, your anti-gradient. It's the evaluation at the end minus the evaluation at the beginning. Compare this, by the way, to the fundamental theorem of calculus. So if you want to consider the fundamental theorem of calculus, that's almost the exact same thing, isn't it? This is the integral from a to b of the derivative of f t dt. That's the original function f from the endpoint minus f from at the beginning point. It's pretty much the exact same thing, only it applies to lines, general curves. It applies to general curves in 2 or 3-dimensional space rather than line segments in R1. But aside from that, it's pretty much the exact same thing. Okay, so with that in mind. And when I say, I accidentally zoomed it. I don't want to zoom this. When I say it's the fundamental theorem of calculus, I really do mean that. It really is just the regular old fundamental theorem of calculus. And to see why, let's suppose that we're going to let z be our function fxy. And let's say that r of t is the vector function xt comma y of t. So the upshot of this is that f depends on x and it depends on y. But each of x and y depend on t. So if you want to talk about the derivative of f of r of t, well, that's the derivative, and just to rewrite this slightly, of f of x of t comma y of t. Thinking all the way back to chapter 14, you can do this using the chain rule, right? This is the partial derivative of f with respect to x times the derivative of x with respect to t plus the partial derivative of f with respect to y times the derivative of y with respect to t. Again, that's just the chain rule that we saw before. However, we also notice that that's actually a dot product, right? That's the dot product of fx comma fy dotted with x prime t, y prime t. Or in other words, the gradient of f dotted with r prime of t. So if you want to look at this problem, in this case, this is the integral over c of the gradient of f dot dr. Well, what's that going to be? Applying our regular formula to that, that's the integral from a to b of the gradient of f dotted with r prime of t dt, which in this case is the same thing as the integral from a to b of the derivative of f of r of t dt. And that really just is the regular, that really just is the regular fundamental theorem of calculus. We just looked at this just 2 seconds ago. This is f of r of b minus f of r of a. And if you're thinking about, if you're working in, I don't know, if you're working in the xy plane, and let's say here's your curve C, and over here we have r of A, and over here we have r of B, and that's the direction we're going in along that curve. Well, really, that's just the same thing as f of the ending point minus f of the starting point. And that's pretty much all there really is to it. Okay? Now, what does that mean physically? Physically, what that's telling us is that the work done by a conservative vector field, it's the same thing to the change in the associated potential energy. Now, for those of you who have taken some kind of physics or classical mechanics classes, that may sound familiar. So the classical example of this is gravity. Gravity is a conservative force. It's a conservative force field. And by the way, not for nothing, but the reason we're calling this conservative has absolutely nothing to do with political affiliation, but it has everything to do with the fact that they conserve energy. We're talking about conservation of energy in this case. So gravity conserves energy. It's a conservative force. And the work done is equal to the change in potential energy. So if you start off very high up a mountain and you're rolling down, then the work that gravity does on getting you down that mountain is equal to the change in your height, in your potential energy, basically. And that's the interpretation that we get from something like this. So let's do a concrete example of this. What if we do, what if we want to look at the work done by the force field F is 2xy comma x squared on a particle taking the curve C, where C is the part of the parabola y equals x squared plus 1 from 1 comma 2 to 3 comma 10. And we're going to observe here that our vector field, our force field in this case, is the gradient of the function fxy equals x squared y. And if you don't believe me, just do the gradient. You take the partial derivative with respect to x, you get 2xy. Partial derivative with respect to y, you get x squared. It's the gradient. So just generally a very good idea is to try drawing a picture. And if we did that in this case, just to give us a sense of what this thing actually looks like, say here's our x-axis, here's our y-axis. This is not going to be to scale, but if you want to consider the parabola y equals x squared plus 1, it's going to look something like this, right? So let's say that this is 1, 2, 3. You're going from the, again, this is not to scale. Oops. You're going from the point 1, 2, up to the point 3, 10. So here's our, so in this case, here is our curve. Our curve is going up this segment right here. Now, I've drawn this. Now, it's tempting at this point to say, okay, let's parameterize that curve. But we actually don't need to do that in this case. So the whole observation here that we want to see is that F, our vector field, is already a conservative vector field. We already know that it's the gradient of something else. So the work is just the integral over C over the curve of F dot dr. But in this case, that's the integral over C of the gradient of F dot dr. And by the fundamental theorem of line integrals, that's F of the ending point, which is 310, minus F of the starting point, which is 1, 2. F of 310, in this case, is 9 times 10. F of 1, 2 is 1 times 2, or in other words, 88. And by the way, I just want to point out, we never had to do any dot products. We never had to do any parameterization. We never had to, figure out what F of R of T is. We didn't even have to do any calculus. This was almost as easy. This is almost as easy as it gets. If you automatically know that your vector field is already the gradient of something else, it's a remarkably easy problem to solve. You don't really even need to do any advanced calculation. All of which is to say, if your vector field is a gradient field, if your vector field is conservative, that should make you very happy. So always check. Always check if your vector field is conservative. If it is, you are in a very good spot. And just how good a spot are you in? How can we actually evaluate this. Let's see how we can actually answer that question about how we actually find these things. Well, suppose you've got a vector field and it's conservative. And you know that it's conservative. Then there's an anti-gradient f, anti-gradient meaning some potential function, so that our big F, our vector field, PQ, is equal to fx comma fy, right? That's the gradient, right? That's what it means to be a gradient field. Now, Clairaut's theorem tells us that, that the mixed partials are the same. Fyx is equal to fxy. So if you differentiate q with respect to x, well, that's going to give you fyx, right? Qx, just to make this as clear as possible, Qx equals Fyx, or in other words, Fyx. And Py, same principle, Fx differentiated with respect to y, or in other words, Fxy. So since Clairaut's theorem says that those are the same thing, if your vector field is conservative, then the derivative of q with respect to x is equal to the derivative of p with respect to y. There's a catch here. The catch is that the converse is not necessarily true. It almost always will be, though, but not technically always. So for example, if you say that all dogs are mammals, well, that's true, but the reverse statement, all mammals are dogs, is obviously not true. There are those among us who may wish that were true, but it is not true. So, however, if your functions are defined and continuously differentiable, which is pretty much always going to be the case, if your functions are well defined everywhere and they're always differentiable on all of the plane, or you can actually extend that to R3 if you're dealing with a three-dimensional conservative vector field. Actually, I take back what I said. Ignore that snippet, what I just said. If you're working in 2 dimensions, this will always be the case. You can do a similar test with 3-dimensional vector fields, but it gets a little more complicated, and we'll talk about that when we get to the other parts of chapter 16. Point is, if you have well-defined and well-behaved functions p and q, and the derivative of q with respect to x is equal to the derivative of p with respect to y, then your vector field is conservative. That's the good news, and that's the upshot of all of this. So, and that's our test. To test if it's conservative, we'll just test whether or not qx equals py. So let's consider, for example, our vector field from before. F is equal to y comma negative x. Is it conservative? Well, in this case, pxy is y, and qxy is negative x. Well, the derivative of p with respect to y, in this case, is just the constant function 1. Meanwhile, the derivative of q with respect to x is the constant function negative 1. Those aren't equal to each other. And because these functions are not, these are severely not equal, they're in fact never equal to each other. And because they're not equal to each other, because they're not, these functions aren't equal, the answer is no. So f of xy, which we're defining as y comma negative x, is not conservative. Which is to say, just to reiterate the point, there is no anti-gradient. That's the bad news here. What about this other vector field? We can consider the vector field f is y comma x plus 3y squared. What are we going to do? Well, p of xy is y, and in this case, that means that the partial derivative of p with respect to y is the constant function 1. Meanwhile, qxy is x plus 3y squared. Del q del x, in this case, is also the constant function 1. Aha! These things are the same. And that makes us very happy. So and that makes us extremely happy, and now we're going to find out what the anti-gradient is. So the anti-gradient in this case, well, how are you going to find that? We know that there's some function f and that function satisfies fx is y, and fy is x plus 3y squared. Well, what that tells us, if we just anti-differentiate y with respect to x, that should give us fx, right? Or that should give us just regular old f, rather. And that's fine, that's not hard to do. Xy plus, now here's the catch though. When you took indefinite antiderivatives in Calc 1 and Calc 2, you had to add an arbitrary constant at the end there because, hey, differentiation makes constants disappear. So there could be some constant there. But in this case, it's partial differentiation. And because it's partial differentiation, constants aren't the only things that disappear when you differentiate with respect to x. Functions of y disappear as well. So I can't just say it's a constant. It might not be a constant. It will be some arbitrary function of y, which I'm going to use the Greek letter phi to denote. So fxy is x times y plus some arbitrary function of y. So, and the important point here is that phi is a function of y alone, not of x, just y. So now, meanwhile we have that, what else can we say? Well, if we differentiate that with respect to y, we know that fy is x plus 3y squared. We also know that it would be the partial derivative of xy plus phi y, which would be x plus phi prime of y. Aha, well, if that's the same thing as x plus 3y squared, that means that phi prime of y is 3y squared, which is to say actually that phi of y is equal to y cubed plus some arbitrary constant k. In this case, I really do mean a constant because phi of y only depends on y, not on x. Phi cannot depend on x whatsoever. And yes, it's true that if you differentiate with respect to x, that things with respect to, yes, it's true if you differentiate with respect to y, then terms that are only in terms of x will disappear. Yes, that's true, but phi doesn't depend on x at all. So the only things that will disappear when you differentiate will really be constants. So the upshot, so you know what phi is, you know what f is now. So we now can say that fxy is xy plus y cubed plus some arbitrary constant, which I'm calling k. Now most of the time we're not going to care what that constant is, because as soon as you apply the fundamental theorem of line integrals, that constant's going to disappear, right? That constant is going to get subtracted off on both sides, so it's not going to matter, but I'm just including it in the interest of completeness in this particular case. So how exactly do you find an anti-gradient? Well, these are basically the steps. You set fx to be equal to p, because just to recall, we're dealing in this particular case where you have that fxy is some vector of functions pxy comma q xy, and that's fx xy of yxy. So set fx equal to p, and then anti-differentiate with respect to x and add a function gy. Here I called it gy. Before I called it phi y. The symbol obviously doesn't matter at all. You differentiate that with respect to y, and then set that equal to q, right? So that's the whole point here is you get f of xy is the integral of pxy, or the antiderivative rather, dx, plus some arbitrary function g of y. Fy, meanwhile, is, well, it's the same story, right? You differentiate this with respect to y, but then you get g prime of y at the end. And that's going to all be the same thing as qxy. And you solve for g prime of y and then g of y, and that's basically it. And check it. The beautiful thing about this area of mathematics is that you can always check your work relatively easily. So let's go backwards. Let's go backwards for a little bit. We'll take another look at our gradient from before. We said that f of xy, we said that that was xy plus y cubed plus some constant k. Well, fx is going to be y. And yes, that is indeed pxy. So that's good. Fy, meanwhile, is x plus 3y squared, and that is indeed our function qxy. So that's good too. The point is you can always check this. You can always check your work. That's the good news here. Mostly it's good news. Everything we're doing at this point in the semester, it's mostly all good news. But what happens if you try this with a vector field that's not conservative? Maybe it can still work out. Well, let's see what happens. 1 second. In this case, what are we going to get? Well, pxy is y. And if we're claiming that fxxy, if the derivative with respect to x is equal to y, and we're also, it's a weird ampersand. Why can I not draw? There we go. And if the derivative with respect to y is negative x, what are we going to get? Well, fxy, maybe you can see where we're going already with this because I did do this yesterday. The antiderivative with respect to y dx plus some arbitrary function g of y, which is xy plus some function g of y. And again, the important point here is that g depends only on y. It can only depend on y. Now, strictly speaking, I should use the same font or the same case. Only depends on y. So fy, meanwhile, which we're saying is negative x, well, actually, that's going to be the derivative with respect to y of xy plus gy. And that's going to be x plus g prime of y. And again, that's equal to negative x. Well, wait a minute, we're in trouble now. What does that mean? That means that g prime of y, which again only depends on y, is actually equal to negative 2x. And that's obviously wrong. That is obviously wrong because, and I think it's obvious in this case because this depends only on y. And this depends in part, in fact, in its entirety, but in particular, just in part, this only depends on x. Actually, hold on. I sort of said two different things at once. Let me try that again. In part, this object depends on x. And that's not good. So that's not going to work for us. So that's the contradiction. Now here's the upshot with some of this stuff. If you have two different curves and they've got the same starting and ending points, and F is a conservative vector field, then if you take two different integrals of the same vector field, of the same conservative vector field over those two different curves, you're going to get the same answer. So suppose, for example, here's one endpoint, here's the other endpoint, here's C1. We're going in this direction. Let's say this is the point AB. This would be the point CD. But meanwhile, if you have some other crazy curve and it's doing some other god-awful thing, but it's going in the same direction with the same endpoint, the same endpoints in this case, no matter what happens, it's still going to be the same. So if that's C1, this is C2, the endpoints are the same in this case. No matter what your function is, no matter what your vector field is, your vector field is important. Your vector field has to be conservative. But no matter what your curve is, it'll still be little f of CD minus little f of AB. It's path independent. Some textbooks and some mathematicians define that to be conservative, that it doesn't depend on the path you take. So all of these are different ways of describing the same kind of general notion, that's path independent. Right. Another consequence of that, which is in some ways also quite incredible, is that if your curve is closed. I mentioned this briefly, that weird things can happen if your curve is closed. You get some other nice shortcuts. Here's one of them. If your vector field is conservative, and if it's not, you can't do this. But if it is, that means that the endpoints are the same. You're dealing with a closed loop. Your endpoints are the same in this case. And if your endpoints are the same, what does that mean? That means that this is going to become f of AB minus f of AB, which is 0. So different ways of, different consequences really of seeing when two curves are path independent and when their endpoints are the same, you get 0 for the integral. And that has a little bit to do with what makes closed loops so special, and we'll look at that next week. But again, this particular aspect only works if you have a conservative vector field. And most vector fields aren't conservative. Now you can do this in 2 dimensions as well. In 3 dimensions as well, although it gets a little bit trickier computationally. Let's find an anti-gradient here. Okay, well, we know that in this case, here's fx. We know we've got an fy. And we know we've got an fz. We know that these, we're told that this thing is conservative, and we get different, we can find out what its anti-gradient is by looking at its partial derivatives. So we know that f is the antiderivative of yz plus 2x dx, which is xyz plus x squared plus some arbitrary function g that depends on y and z, because both of those are going to disappear when you differentiate with respect to x. So let's differentiate that with respect to y. That's going to give us xz plus gy yz. But that is going to be xz plus 2y plus z. And that tells us that gy yz is 2y plus z. So we need to know what g is now, so you can find out g by anti-differentiating this with respect to y. So g of y and z is the antiderivative of 2y plus z with respect to y. And that's going to become y squared plus yz plus some other function h, which only depends on z, because again, z terms are going to disappear when you differentiate with respect to y. But if you differentiate g with respect to z, what do you get in that case? Here's a better question to ask. Rather than saying what's going to be gz, what we know now at this point is that f of xyz is xyz plus x squared plus y squared plus yz plus hz. So now we can just differentiate with respect to z. And that's going to give us xy plus y plus 3z squared. Differentiating the above with respect to z is going to give us xy plus y plus h prime z, which tells us that h prime z is 3z squared, or in other words, hz is equal to z cubed. So we know g and we know h, and at that point, we're ready to say what exactly our anti-gradient is. fxyz is given by xyz plus x squared plus y squared plus yz plus z cubed. And if you want to be really precise, you can include an arbitrary constant of integration at the end of it. That's about it. And that's how you find the anti-gradient. Now, strictly speaking, did we know that fxyz was conservative? Well, not using the techniques we did before, because the techniques we used before, really those only told us about what happens for two-dimensional vector fields, not three-dimensional vector fields. Fortunately, there is a way to determine what happens with three-dimensional vector fields as well, using something called curl. And we'll look at curl probably at some point next week, or maybe the following one. I'm not sure which. Oh, wait a minute. So the strategy for finding for finding the anti-gradient of a three-dimensional vector field that you know is conservative, it's pretty much the same thing we just did, right? You set fx equal to p, anti-differentiate with respect to x, and then you add a function gyz, differentiate that with respect to y, and set that to q. Solve for gyz, anti-differentiate with respect to y, and add a function hz. And then you would rewrite your f again, and set that equal to r after you differentiate with respect to z, and then solve for h prime of z and then z, and that's basically it. And of course, check it. It's pretty much the same exact idea, just with an extra iteration of a step. And you can keep on doing this forever, until the cows come home. So let's do one more example of this. This vector field is conservative. The vector field in question is the vector field in question is obscured by my control panel for the thing. So I'm going to try to move this around a little bit. Okay, so the vector field that we have is sine yi plus x cosine y plus cosine zj minus y sine zk. That's conservative. So we want to know what the integral of f dot dr is. Now I want to point out, by the way, what happens if you try doing this directly. This is worth pointing out. So now you might ask yourself, well, wait a minute, we already know how to do line integrals of vector fields. Why do we have to find this other way of doing it? Well, let's see if you try doing it the original way. F dot dr, after all, is the integral from, in this case, it would be 0 to pi over 2 of f of r of t dotted with r prime of t dt, which in this case would come out to what? This would come out to integral from 0 to pi over 2 of, let's get ready for this, sine of t I plus sine t cosine t, sine t cosine t plus cosine of 2t j minus t times sine of 2tk, all of that dotted with cosine ti plus j plus 2k dt, which is the same thing as the integral from 0 to pi over 2 of sine t cosine t plus sine t cosine t plus cosine 2t minus 2t sine 2t dt. Is that possible? Can you do that? Yeah, sure you can, but it would get a little computationally a little bit annoying, especially because this last term over here, this last object, you would have to integrate by parts. And while that's possible, it's kind of annoying. So if there's a way that we can do that without having to go through this huge, massive calculation, that might be a little bit preferable. So let's try doing it that way. Let's try doing the slick approach with the fundamental theorem of line integrals. We know that thing is conservative, so we know that fx is sine y. That tells us that f is the integral of sine y dx. And that means in this case that we know that, wait a second, we know in this case that that means that we're dealing with x sine y plus some function g of y and z. Fy is x cosine y plus gy yz. And we know what that is. That's x cosine y plus cosine z. So that tells us that gy yz is cosine z, which tells us that g yz is y cosine z. Okay, so fxyz so far is x cosine y plus y cosine z, and I forgot something important, plus some other function hz, which I still don't know. But I do know that fz is x cosine y plus, sorry, that part goes away actually. It would be negative y sine z plus h prime z, which we're told is negative y sine z, which tells us that h prime of z is some, is 0. So h of z is just some constant, which it turns out we're going to be able to ignore. So the upshot of all of this is that fxyz is just going to be x cosine y. I'm sorry, I forgot something. X cosine y plus y cosine z plus some constant k, which I don't really care about. Now, what about the endpoints? I know that r of 0 in this case is just 0, 0, 0. And I know that r of pi over 2 is I plus, is 1 pi over 2 pi. So the integral that we're interested in, f dot dr, is little f of 1 pi over 2 pi minus f 0, 0, 0, which in this case is going to come out to cosine of pi over 2 plus pi over 2 cosine pi plus k. Actually, make it a capital K to just be consistent. Minus k. That's f 0, 0, 0. Cosine pi over 2 is 0, 2. Cosine pi is negative 1. This whole thing comes out to negative pi over 2. And I submit to the jury that that is an easier thing to do than going through the whole integration by parts mess and use substitutions of the various cosines and things like that. This, I think, is a little bit slicker. So we're trying to help you develop a toolbox of different techniques to use to be able to solve different kinds of problems. So hopefully this, during recitation this week, we'll do lots of examples of different kinds of line integrals, and we'll see what kind of approaches make sense for different kinds of problems. All right, so I hope this was informative and that you enjoyed this, and I will see you guys on Wednesday.